It's my great pleasure to introduce Zhiyao Duan, who is a professor at University of Rochester. He did his PhD at Northwestern, finished in 2013, and then moved to Rochester right away. When I invited Zhiyao to come, he asked me what I wanted him to talk about. And it's really hard because he's done so many great stuff in pretty wide array of things, like audiovisual stuff, like recently like neural fields for spatial audio. So it's hard to pick. So I let him pick, and he chose to talk about frontiers of speech synthesis. So take it away. Yeah.
All right. Thank you very much, Jonathan, for the invite. Thank you, John, for organizing the event. So it's really my great pleasure to present at SANE. SANE is one of my favorite workshops. Every year I don't have to push my students to attend the workshop. They just always want to come. And they drive to SANE. That drives me insane because I have to find money to support them. Okay, so as Jonathan said, in our lab, we actually do a lot of different research. We work on music information retrieval, music transcription, source separation, music generation. We also work on speech processing in recent years. We work on speaker verification, anti-spoofing, and also speech synthesis, like voice conversion, text-to-speech. And we also work on general audio, like sound retrieval through vocal imitation or audio text models. And we also have collaboration with computer vision researchers on audiovisual processing, like audiovisual analysis of music performance and talking face generation. This is a demo. The technique is outdated. It was like 2019, but we were among the early works on talking face generation. So my student asked me to rap. Let's see. Oh, okay.
When you chill, living with your parents, never chipping for the bills. You need to scrub the dirty dishes in their kitchen out for real. This is just your life. Listen if you want. Don't just spend your whole day on the sofa hitting blunts. You were on the back of the line right now. Got to progress, got to move. You got to work so we can get you to the front. All right.
So this audio works. That's great. So today I'm going to talk about speech synthesis. And first, I want to play you some audio so that we can appreciate how long a way that we have come for the decades, right? So first, I will present you this digitized vocal tract analog model. This is a Daisy Bell song. This was synthesized in the 1960s.
Daisy, Daisy, give me your answer, ooh. I'm half crazy, all for the love of you.
Okay, I think that's enough. Is the audio volume okay? From here, it's a little weak.
Maybe a little higher.
Okay, I think I'm at max here.
Turn it up to
11. All right, I'll try. So the next one is in the 1990s. This is from AT&T, and this uses concatenative synthesis.
Hi, this is Mel, the new AT&T natural voice available from www.nextup.com. With 16 kHz sound quality built on the world's best text-to-speech engine.
Okay, that's the best at the time. So they have, they have large corpus of small snippets of speech, and they have a unit selection module to select the appropriate units to concatenate them together. And then this one is HMM-based system. This was a model in 2010. So this is a demo from Festival Text-to-Speech.
I like the SANE workshop very much.
Okay, it's better. And then, deep neural networks came. This is a WaveNet demo.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
Much more natural, right? And this is variational inference, WITS model.
The prisoner had nothing to deal with but wooden panels, and by dint of cutting and chopping, he got both the lower panels out.
Higher quality now. And then latent diffusion model from Microsoft.
Indeed. There were only one or two strangers who could be admitted among the sisters without producing the same result.
Okay, so we have come a long way. If we just focus on the quality or naturalness in a short time, sometimes it's even hard to distinguish from real human speech. But now we are at the new frontiers of speech synthesis, right? What should we work on in the next decade, let's say? So we know that speech is mainly for communication for humans. We need to use speech to communicate the words, the semantics, the emotion, and attitude. And when we do the communication, we have different ways of speaking. So the way I speak to my kids is different from the way I speak to my mom. It's also different from the way I speak to, say, a taxi driver. Okay, we express different emotions, we have different ways of speaking, and we express different contents. And so this requires the controllability of a lot of aspects of speech when we communicate. And this also requires that the speech synthesis model to be able to cover a wide range of paralinguistics if we want the AI model to be having a conversation with humans. And also the AI model needs to be able to converse naturally to produce natural conversations. So in the past decade, some research, there has been quite some research on these issues, controllability, expressiveness, and natural conversation generation. I do not want to give you a comprehensive review of those work, but here I want to give you a bird's eye view of the state of the art. I definitely have left out a lot of work, but here, at a very high level, on controllability, we have seen work on controlling the emotion, the style, the accent, and prosody. But we can say that most of the controls were through categorical labels or maybe natural text, natural language. Right? On expressiveness, the research has been focusing on the emotion and style, say through the categorical label control to generate different emotions in a speech, or mimicking different styles, say the minions or different characters in movies. And on natural conversation generation, there has not been much work. Okay. So today I want to introduce several work in our lab in recent years, and we approach these three problems from some unique angles. The first project I want to introduce is called ControlVC. It's a zero-shot any-to-any voice conversion that allows time-varying controls on pitch and speed, the parameters that we really understand. And the second project will be GTR-Voice. It's a data set and also initial study on expressive TTS at the articulatory level, not at the emotion or style level. And the third one is Parakeet. It's a highly natural conversational TTS model. It's an end-to-end model, a large model. So I'll go into the three projects. I'll spend about 10 minutes on each. So first, ControlVC. So voice conversion is to convert one person's voice to another person's voice without changing the words, roughly speaking. Now, the motivation of our research is that, when we think about the use case of voice conversion system, you can do bad things like generating deepfakes to spread misinformation. But if you think about the positive use cases of voice conversion, I think the major use case is multimedia production. Say you are a vlogger and you want to do voiceover. Maybe you do the voiceover yourself, but you want to beautify your voice to make your voice sound more interesting, right? But we know that audio engineers prefer explicit control on human interpretable parameters. They don't want to just use a black box and lose control of it. So our design goal is to achieve time-varying control on pitch and speed, these two important parameters that audio engineers would like to manipulate. Okay. So how do we actually control through this system? Well, you can simply input a control curve on speed and also on pitch. So the left figure shows this speed control curve. The vertical axis tells us the ratio of the controlled generated speech, the speed compared to the original source speech. So we can see that in the beginning, the speed is half time as a source speech, and then it increases speed, and toward the end, it decreases speed. The right figure shows the pitch control. We can see we want the pitch to be the same relatively compared to the source speech, and towards the end, we want the pitch to raise. So making this sentence more like a question. Now, what's the key idea of our approach? Well, our approach, the key idea is to integrate signal processing and machine learning techniques. We know that signal processing techniques are more interpretable, and they allow us to have explicit controls, but they often generate unnatural and low-quality speech. On the other hand, machine learning models are black boxes, and perhaps they allow us to do implicit control in the embedding space, but they can generate natural and high-quality speech. If we join these two techniques together, we can have a hybrid model to have the best of both worlds. So in this system, we perform two steps. In the first step, we modify the pitch and speed using the control curve using signal processing techniques. And then in the second step, we use machine learning or deep neural networks to perform the conversion, to change the voice to another person's voice, and also to smooth out those artifacts. We choose this order of processing because if we reverse the order, then it would introduce much more artifacts into the final result. So what are the key challenges of this model, right? We know that there's a heavy burden imposed onto the neural network because the neural network needs to be able to respond to the modified pitch, which may not be natural at all, okay, because the control curve may be arbitrary. It also needs to be able to keep the time-modified linguistic content of the source utterance because it cannot change the content. It's voice conversion. And also it needs to be able to incorporate the speaker timbre from the target speaker. And then it needs to fuse all these three aspects together to generate the converted speech and smooth out artifacts. Now this requires disentangled representations. We need to disentangle pitch, content, and also timbre information. Okay. This is our architecture. Here we have two parts. The blue shaded part are pre-trained models to have those disentangled representations. And the green shaded part is a synthesis model that we train on this task to generate speech. And the input would be the source speech, and we apply the TD-Pisola technique to change the speed, and then we apply the pitch control curve to modify the pitch. Okay. So let's go into the modules. The first one is to apply pitch and speed control. So we apply TD-Pisola to the source speech to modify those, to modify the speed. And then we extract the pitch contour using YAPT and multiply it with the pitch control curve. Here we perform this at a frame length of 20 milliseconds and hop size of 5 milliseconds. And then we pass the modified pitch contour to an VQ-VAE encoder and vector quantization to obtain the pitch embedding. Okay, so this VQ-VAE is trained on the original utterances without any pitch modification through MSC loss for pitch contour reconstruction. So this VQ-VAE is to encode the modified pitch contour into those embeddings. The second module is this linguistic embedding. And here we use Hubert, and we pass the speed-modified source utterance to a pre-trained Hubert model. This model was pre-trained on 960 hours of Libre speech. And we extract feature vectors at the 6-layer output with the same frame rate as the pitch so that we can later concatenate with the pitch embeddings together. And then we map the vector to the closest cluster centers, which were learned through k-means clustering. So that's the linguistic content, also extracted from the source speech. And the third module is speaker embedding. This is extracted from the target speech to learn the target speaker's timbre. And here we use a simple 2-layer LSTM network, taking the spectrogram as input. And we train this model on 3,500 speakers from the VoxClub and Libre speech dataset using the famous GE2E loss on speaker classification. And then we extract the 256-dimensional speaker embedding vector. Okay. So these are the three modules. And then we concatenate those embeddings, the pitch embedding, the linguistic content embedding, and the speaker embedding together, and pass that to this hi-fi gun vocoder. And the hi-fi gun vocoder is trained on this task, on this voice conversion task. Okay. So yeah, now I will show you some demos. So here I'll play you the source utterance, and then the target speaker's voice, and then I show you the speed control curve or the pitch control curve, and then play you the converted voice. Okay, so the first one, source utterance.
The difference in the rainbow depends considerably upon the size of the drops, and the width of the colored band increases as the size of the drops increases.
Then the target voice.
John Prescott is John Prescott, as the Prime Minister would say.
Okay, and then we apply this speed control curve, so the speed should decrease gradually, and the converted speech.
The difference in the rainbow depends considerably upon the size of the drops, and the width of the colored band increases as the size of the drops increases.
Okay, the speaker is falling asleep. And another demo, so the source speech.
Or so everyone believed.
And target voice.
It seems so long since I did the exams.
Okay, female to male conversion. And we apply this pitch control curve where the pitch should suddenly increase and gradually decrease at that moment.
Or so everyone believed.
Okay, so now we achieve this emphasis effect. We emphasize the word achieved, right, or believed. Okay, so we conducted...
The difference in the rainbow depends considerably upon...
Or so... There's a concert of speakers. Anyway, so we conducted some user studies or listening tests. Here we perform experiments on this VCTK corpus. We train on 100 speakers, and we test on 90 pairs of 10 unseen speakers, 5 male and 5 female, speaking unseen utterances. So we achieve zero-shot any-to-any conversion. And we also compare with our own constructed baselines. One is called P-LPC, which is using TD Pisola plus LPC synthesis technique. The other one is P-AutoVC, which is using TD Pisola to change the speed and pitch, and then we pass it through a pre-trained AutoVC model for the conversion. And regarding the control curves, we generate 2 kinds of pitch control curves and 3 kinds of speed control curves. So the top 2 figures show the pitch control curve. One is stressing, one is rising at the end of the sentence. For the speed control curve, we have the speed up, slow down, and also the parabola to speed up and slow down. Okay. So here are some objective evaluation results. We first evaluate well the converted speech still preserves this speaker similarity with the target speaker. Right. For ground truth data, we should have cosine similarity of 1. And we also assess the word error rate to make sure that the converted speech does not degrade the speech intelligibility of the original source speech. So here we have 4 settings: no control, pitch control only, speed control only, and pitch plus speed control. And we compare with the baselines P-LPC and P-AutoVC. We can see that across all these settings, our proposed method achieves better speaker similarity to the target speaker, and also achieves higher or lower word error rate compared to the baseline models. And then we conducted user studies or listening tests. So the first test here is to evaluate the naturalness and timbre similarity. Basically, we present listeners the source speech, the target voice, and the converted voice, and we ask them to rate the quality and also, the naturalness and also timbre similarity. And here are the results. We can see that the proposed method, which are the dark blue bars, are much higher in terms of mouth scores on naturalness and also similarity to the target speaker than the other 2 baseline methods. So this sets a foundation for our next experiment, which is to assess the controllability of this model. Now, for controllability experiments, we present listeners the source utterance and the converted utterance together with a control curve on pitch or speed. And the control curve has a chance to be a wrong curve. I think there's a 15% of chance to be a wrong curve. Okay. And then we ask the listener to rate whether they think the converted speech follows this control curve or not. So they use a slider to rate how accurate the control is. And this is a result. So you can see that we have pitch-only control, speed-only control, and pitch plus speed control. And there are 2 cases I mentioned. We can present the real curve to the listener, and sometimes we present the fake curve to the listener. In both cases, they don't know whether it's real or fake, but they need to rate how accurate the control is. You can see that for pitch-only control, when we present the real curve, they think that the accuracy, they rate that to 3.38, which is statistically significantly higher than when we're presenting the fake curve to the listeners. And the same observation is obtained on the speed-only control. So when we present the real curve, the ratings is significantly higher than when we present the fake curve. And in the pitch and speed control setting, we only present the real curve. We didn't compare with the fake curve because there will be 3 kinds of fake curves. Either pitch is fake or speed is fake or both are fake. That's a little complicated. Okay, so that's the first part of this work, of this talk. And we presented a zero-shot any-to-any controllable voice conversion system to control the pitch and the speed in time-varying fashion. Yes, a question?
Is it okay to ask questions in the middle, or we'd rather not?
I mean, but it's quick. It's fine.
I'll be quick. Yeah, so your model has a separate, the pitch trajectory is modeled in a separate module versus the speaker modeling.
Mm-hmm.
So when I think about certain speakers, though, their pitch trajectories are inseparable to my mind from what they're saying. So when I say, oh, that was a really huge thing, it wasn't a huge thing as some other public figure might say. Donald Trump, for example, would say he would do pitch and stress on the word huge. So how is it the correct decision to model pitch contour as a property of the utterance rather than as a property of the speaker?
Yeah, so that's actually exactly one of the motivations of this research. Because if we don't control the pitch, then we convert it to a speaker and we lose the control of the pitch, and the converted result may not be natural. Now we can control the pitch at every moment. We can make it more natural. And here we are inputting the pitch control curve, not the pitch contour. We're inputting the, how many times, how much higher the pitch should be, basically. Yeah.
Thanks.
Sure. Thank you. So now I'm moving on to the next project, that is GTR-Voice. It's a dataset and initial study on expressive TTS at the articulatory level. So we know that expressive speech synthesis, it needs to capture a wide range of paralinguistic features. Paralinguistic features contain a wide range. At the low level, it can be articulation and phonetics. Mid-level can be style, and high level can be emotion. And this low-level and high-level expressiveness are actually relatively independent. Say the same articulation method can express diverse emotions. And the diverse articulation methods can carry the same emotion. For the second point, it's actually easy to understand because different speakers have different articulation methods, but they can speak the sentence in the same emotion. But this can also be achieved by professional voice actors when they act different characters. So this GTR-Voice project, the motivation here is that existing research on expressive speech synthesis focuses on emotion and style, but they didn't focus that much on the lower level expressiveness. When we look at the most expressive speech production system on Earth, right, those are professional voice actors, they actually spent years in training their articulation methods. And for example, I have a sentence here, right? The same workshop always drives me insane. And I would like to invite my student, Chris, to demonstrate how to speak this sentence in using a breathy and softer tone, a more languid pronunciation, and a hint of nasality. Maybe you can speak first in a normal, like your normal voice, and then the setting.
What a zero-shot learning task here. I should I should have rehearsed for that. What is this?
So you maybe first read the
workshop always drives me insane. Okay.
Okay, that's your normal.
The normal one is the SANE workshop always drives me insane. And the way. So what do we want to render?
To use a read the sentence again, but using a breathy and a softer tone.
Okay, breathy and a softer tone and more languid pronunciation. A hint of nasality. Okay.
Yeah. Come on, this is from your paper.
Okay. Oh yeah. I told her. It's difficult. Yeah, that's the reason why we spent many years in training these useless articulation methods. Okay, breathy in a softer tone. That means the SANE workshop always drives me insane. And languid, the SANE workshop always drives me insane. A hint of nasality. The SANE workshop always drives me insane.
All right. Okay. Thank you, Chris.
Okay. We probably don't want to ask you. Okay. Yeah.
Thank you, Chris.
I want to waste time.
So our goal is to investigate we'll listen to more demos from him. So the goal of our research is to investigate expressive speech synthesis from the perspective of articulatory phonetics, and then test its feasibility of its controllability. Okay. So Chris actually recorded a data set, and he first defined this problem. At this low level, he defined 3 dimensions: the glottalization, the tenseness, and also resonance. For each dimension, you have several scales or levels, right? And in total, there were 125 combinations across all the 3 dimensions. And he recorded all these combinations on 20 Chinese sentences. That resulted in 2,500 utterances, totaling 3.6 hours. And he's a professional voice artist. He was able to speak, language in the 125 different kinds. That's really awesome. Yeah. Well, you wrote that in the paper, so. And we recorded this in a professional recording setup, and the data set is fully accessible. So now we also did careful evaluation of the labels. So we had human evaluation of the labels. We have 3 speech processing researchers who are the other 3 student authors on the paper. Were asked to label 50 random utterances, taking the recordings of all these 125 combinations of 1 sentence from the data set as reference. And then they evaluate against the ground truth labels. Along the G and T dimension, we do this Pearson correlation coefficient, and that's 0.75 or 0.8. That's pretty good. Along the R dimension, which is not order dimension, we do the classification accuracy, and we achieve 0.78. That's pretty good, too. And we also perform automatic classification using a multi-class SVM classifier. And we take the traditional features like MFACCs and the spectral features for each dimension to do the classification. And the classification accuracy is about higher than 0.8. Remember, this is a 5-way or 7-way classification. So it's pretty good. So this validates the labels or the consistency of the labeling, the recording process. Here I will show you more examples. Chris actually implemented a cool interactive cube on the web. You can actually rotate the cube and click on each square to listen to those voices. Now let me just play you 4 different voices. The first one is, glottalization is slack voice, tenseness is slightly lax, and the resonance is chest voice. And this is a Chinese sentence.
中国的木偶剧院来坦桑尼亚表演，尚属首次。
Okay, now let's make the tenseness to be the tensest. Okay, but the other dimensions remain the same.
中国的木偶剧院来坦桑尼亚表演，尚属首次。
Okay. Another one. So 2, 3, 6. 2 is modal voice. 3 is moderate tenseness. 6 is chest head nasal mix resonance.
中国的木偶剧院来坦桑尼亚表演，尚属首次。
And the last one, modal voice, moderate tenseness, and chest nasal mix.
中国的木偶剧院来坦桑尼亚表演，尚属首次。
Right? How cool is that? It's hard to imagine that these voices all come from one person. Okay, so then using this data set, we constructed 2 models for text-to-speech. And one model is based on fast pitch, and we call this GTR fast pitch. So this diagram shows the fast pitch architecture. It has this FFT block, the feed-forward transformer blocks, and it has this pitch predictor and duration predictor. And what we do here is we add a GTR embedding to the output of the FFT block. And then we fine-tune the entire network on the GTR-Voice dataset. Okay. After this fine-tuning, this model is able to generate Chinese Mandarin speech. Another model we construct is based on style TTS. This is the architecture of the style TTS. The training process of style TTS has 2 stages. The first stage is to train the text encoder and style encoder, and then the second stage is to train the whole thing here. So what we do here is we take the style encoder, the pre-trained style encoder, and fitted with the so-called GTR embedder. The embedding network is trying to predict the pre-trained style encoder's output. Okay, and then we replace that style encoder with this trained GTR embedder as input. So now we can input GTR labels into this style TTS system to generate GTR-controlled text-to-speech results. So after training, this model is not fine-tuned on the rest of the network, and it generates English because the style TTS was trained on English speech data. So now let me show you some examples of the generative speech. So again, first is a reference. Oops, my battery is low. Give me a sec. I need to have a cable here. Do we have a plug somewhere? Okay, yeah, there is one. Great. Thank you. Okay. Oh, I'm not sure if it is working though. Okay, yeah, I think it's working. Let me see. Yeah, it is working. Okay, sorry about that. So let's take a listen. First, a reference.
中国的木偶剧院来坦桑尼亚表演，尚属首次。
Then fast speech on unseen text.
不能将政府应当承担的补贴作为财政包袱甩给老百姓。
Okay, the quality and naturalness is not very good, but the GTR concepts are learned here, right? And style TTS.
But for this, I might have been quite a different man.
Okay, the quality is a little better. GTR is also learned. Now this a different GTR combination.
中国的木偶剧院来坦桑尼亚表演，尚属首次。
And fast speech output.
不能将政府应当承担的补贴作为财政包袱甩给老百姓。
Style TTS.
But for this, I might have been quite a different man.
Okay. All right. So we conducted subjective evaluation on these outputs. We had 60 online listeners, and each of them listened to 18 to 19 trials of one model. And they evaluate on the GTR controllability, speech quality, and also naturalness. Each trial tests one dimension, and it includes one reference utterance of the intended GTR value from the GTR-Voice dataset. And it also includes 3 generated utterances. One has an intended GTR value, while the other 2 vary along the tested dimension to the closest value. For example, if we test the G dimension and the intended G value may be 3, we will present a generated speech having a value of G equals to 3. And also, we have 2 other utterances generated with G equals to 2 and 4. Okay. Then the listener will choose which one is the most natural. Let's see, which one carries the intended GTR value. Okay. After choosing that, the listener also needs to rate how is the quality and how natural is the utterance. So here's the result. First, the quality and naturalness result. So this is a MOS score. We can see that both models achieve a MOS score higher than 3.0, which is fair, or better than fair. So this lays the foundation for the next controllability experiments. If the quality is too bad, then there's no meaning to do the controllability experiment. And we also observe that style TTS achieves a higher MOS score than fast pitch. We remember that style TTS was only the style embedder module was fine-tuned on the GTR-Voice dataset. But for the fast pitch, the whole network was fine-tuned on the GTR-Voice dataset. This suggests that fine-tuning actually hurts the synthesis quality and naturalness, probably because this dataset is too small. It's only on single speaker and with limited utterances. So then we move on to the controllability experiment. So we ask the listener to have this three-way classification, right? And we can see along the G dimension, they achieve a classification accuracy around 60%. Remember, the random guess would be 30%. So this shows that it is somewhat distinguishable. And we also see that fast pitch achieves higher controllability than style TTS. And this suggests that fine-tuning on GTR-Voice does help to learn the GTR concepts. Right? And we also have results along the other two dimensions, tenseness and resonance. And in all the dimensions, we can see that the fast pitch achieves higher controllability than style TTS. And when we compare the three dimensions, we can see that the resonance dimension is more controllable than the tenseness and glottalization dimensions. Okay. So summary of this work, here we proposed three dimensions to model speech expressiveness at the articulatory level. And we recorded a data set. We also tested the feasibility of GTR control in text-to-speech. For future work, we would like to extend the study to multi-speaker GTR controllable TTS, and we would also like to improve the quality and controllability trade-off. Okay. So the third project is Parakeet. This is different from the previous two projects, which were like small data projects. This one is like big data project. This is a conversational TTS model. So here, our motivation is that existing TTS research has been focusing on monologue generation. Our goal is to develop a model that can produce natural conversational speech. And we also would like to generate common events such as laughter and coughing. And we would like to have a simple architecture end-to-end model. So the data we use includes 60,000 hours of Spotify podcasts, 30,000 hours of audio books from LibriVox, and 3,000 hours of Common Voice English subset. So here I show you some demos. The input text would be the rich text, including a speaker ID and also some kind of events. Let's take a listen.
Okay, now I'm going to demo this text to speech system.
Mm-hmm.
The speech you're hearing right now isn't real. It's fake.
No, that's hard to believe.
I'm serious.
Yeah, you can have this kind of disinfluences here. And the next demo.
What's sort of cool is that you can produce coughs if you have to.
What do you mean?
Well, there, I just coughed.
So when I type cough, it doesn't say cough. Right, okay. So another, this model can also do voice cloning. If you provide a few seconds of audio from one person, it can just learn and continue that text. So if the input is...
Because I want to just, if you want to talk about Trump, we can talk about Trump. But if you just talk about Biden, I don't think comparing him to Trump does anybody any good.
Okay, so now let's listen to the continuation, and including the original utterance.
Because I want to just, if you want to talk about Trump, we can talk about Trump. But if you just talk about Biden, I don't think comparing him to Trump does anybody any good. Okay, time to stop talking about politics and start talking about AI. Did you hear about this new text-to-speech system? They call it Parakeet.
Okay, cool. So the model architecture is very simple. It's a transformer architecture, and we have a text encoder taking the rich transcript as input, and then it tries to predict the DAC or discrete audio codec tokens. And then we use the DAC codec decoder to decode the waveform. So, but training this thing takes time because the Spotify podcast data has transcripts, but they are noisy. We have to clean those transcripts. The way to do that is have multiple steps. In the first step, we fine-tune a Whisper V2 large model to obtain a so-called Whisper D model. This is for dialogue. And this model is able to transcribe conversations with both speaker IDs and those common events. And this step actually contains two small steps. The first step, we fine-tune this Whisper V2 large model on 20 hours of audio with automatic transcriptions, with those rich transcriptions. And in the second step, we further fine-tune it on the two hours audio with human annotation. Those are really accurate labels. And after this fine-tuning, the Whisper D model is able to generate very accurate text.
It's very important that your spouse is supportive and willing to sacrifice, because it is a sacrifice to be a coach's wife or husband. And so, I heard coaches say that when I was young, before I was married, that, your wife.
Okay, that's enough. And then in the second step, we just take this WhisperD model to transcribe all the audio data we have. Okay. And then in the third step, we compute the DAC codecs or tokens. What we do is we use a pre-trained DAC encoder, and we generate 86 latents per second. Each latent has 9 codes, from low level to high level, and the low level codes contain most of the semantic information. Okay. And this means that every second there are about 700 or 800 codes. That's a lot. Imagine 1 minute. That's a lot of codes. So with this input text and also these DAC codes, we just train transformers to map the text to the codes. How do we do that, right? As I mentioned, there are so many codes per second. One naive way is to just linearize all the codes and let transformer to predict, but that's a lot. Another way is to predict the 9 levels of codes independently or conditionally independent on the previous tokens. But this would mean that we assume conditional independence of those 9 levels of tokens. That's not realistic. So the technique we adopt is borrowed from this music generation paper, and we have this delay pattern at different levels. For the lowest level, we don't have any delay, but at higher levels, we delay their tokens, so that the higher level token prediction will be dependent on the lower level token prediction. Okay. So, and another technique we use is called classifier-free guidance. So this technique was originally proposed for diffusion models, and the key idea is that we train a conditional model, and we also train an unconditional model. The conditional model would take the text as condition. The unconditional model would only model the audio token itself, right? And then we modify this conditional model by the difference between the conditional model and the unconditional model. We look at their largest difference, and we scale the difference with the parameter alpha, and we add that difference to the conditional model logics. So, however, this causes an issue. This improves the speech quality, but it makes the generative speech speed up over time. So when you speak a long sentence using the model, in the beginning the speed rate was okay, but gradually it's getting faster and faster. There's some explanation here, because when we add this difference between the conditional model and unconditional model, actually the right phoneme will be enhanced too much. Then the model would have higher chance to choose the next right phoneme. And it gradually always chooses the right one and faster and faster. Okay, so let me play some demos. Without this classifier-free guidance,
I think find your customer, get the product, and sell it. It sounds very easy, right? I understand when people say, okay, obviously that's the most obvious thing to do, but trust me, like 80%.
Okay, so that quality was not very high.
I think find your customer, get the product, and sell it. It sounds very easy, right? I understand when people say, okay, obviously that's the most obvious thing to do, but trust me, like 80% of the entrepreneurs or 80% of the ideas that we hear have this very basic problem, this problem exists in 80% of the cases.
It's faster and faster, yeah? Then we propose a technique called CFG filter. So the idea here is we use this logics of CFG to construct a top K mask for the logic of conditional model. So we still use the logic of the conditional model, but we only use a subset of that instead of everything, right? So we use this CFG logics to construct a mask to choose those subset. And with that, we can...
I think find your customer, get the product, and sell it. It sounds very easy, right? I understand when people say, okay, obviously that's the most obvious thing to do, but trust me, like 80% of the entrepreneurs or 80% of the ideas that we hear have this.
So now it's higher quality, but it doesn't speed up anymore. Okay. So summary, here we trained a highly natural conversational TTS model, and this model has been used to generate training data for conversational speech recognition. And we had a paper in the interspeech workshop, Synth Data for General AI workshop. So you can find more demos on the blog we have. So now I'm out of time. So I want to briefly conclude this presentation. So here I hope that I convince you that the importance of speech communication with AI is increasing as AI enters our daily lives, right? Imagine that robots come to us, and robots, we hope them to carry different roles in our life. And then we need speech synthesis technology that are more controllable, expressive, and are able to produce natural conversations. I think that's the new frontiers of speech synthesis research. So finally, I would like to present 2 job opportunities. One is a faculty position in the Electrical and Computer Engineering Department at the University of Rochester. This position is open to all technical areas as long as the research is relevant to audio and music engineering. And another position is a postdoc position in my lab working on speech anonymization, voice conversion, and speech synthesis. So if you know someone who may be interested, I would appreciate that you spread the information to them. So finally, I want to thank my students who worked on these projects, and I would like to thank Google for providing the very generous TPU computational resources, and also the funding sources that have supported our speech processing research in the past few years. And I thank you all as well. Thanks.
Check, check. Ooh.
Yeah, good.
So given the trajectory of the previous 2 projects and the last project, I guess the natural question is, given that the GTR features were often described in natural language, it seems logical that Parakeet could then take those instructions as natural language and like kind of do the same types of natural and expressive behaviors you had before. Have you explored that? Are you exploring that? Is it something you see as interest? I know there's a lot of overlap, especially in the vision community, with doing these types of expressive labels. So I'm curious to hear your thoughts in the future.
Yeah, that's a great question. So these are all projects we have done recently, and we haven't got a chance to kind of integrate the ideas together. But I also see some kind of contradiction among these projects, right? The last one, the Parakeet, is an end-to-end model and takes the text as prompts or inputs. But the GTR and the ControlVC, they take signal controls, right, or the control labels for the GTR dimensions. So how to integrate them together is actually a question that we need to think about. But that's a great question. Thank you.
Thanks. I'll hopefully be relatively quick, a 2-parter again. The first one, you had the great Daisy Bell example. Daisy, Daisy. Are you aware of any singing synthesis? The latest I've known from the computer music lab where I went was the Perry Cook's singing synthesis and Xavier Roday's formant synthesis. Are you aware of any compelling speech singing synthesis, that has since emerged since this brand new deep neural network era?
Yes. There are a lot of singing voice synthesis and also singing voice conversion systems out there. And for example, the Sovitz is built on a VIS model. They can synthesize singing voices very naturally.
Sovitz?
Yes.
Okay.
And actually, because they are so real, now a lot of users, they upload the deepfake singing voices and mix them with the background music to the web to let singers to sing songs that they have never sung before.
Wow.
And this poses some challenge to the music production industry. And we recently proposed a challenge called Singing Voice Deepfake Detection Challenge. And we call, this challenge will be, is being held at the SLT workshop this December in Macau, and about 60 teams participate in this challenge.
That's great, and that leads into my second question. When I heard your parakeeting of Joe Rogan, I got a shiver, because I realize we're now in this brave new world and there's no going back. And so in France, there's this concept of moral rights. So when I speak in my voice, I have a moral right to my performance of my voice. And no one can take that from me because that would be immoral. And so I'm so glad you're doing the deepfake detection. This is a minor point, but it's unlikely to deter bad hat hackers, but do you put an ethical statement on your papers saying we disavow the use of this technology to violate people's moral rights?
This is a great question. So I see you are, while you speak, you have your recording here. So that's
I know.
That's a proof of your voice, right? That's a great
And in California, it would be illegal for me to be recording you without your permission.
I see. I'm okay. So in our research for the Parakeet model, this is so powerful, and we are fully aware of the risk that it may bring. So that's why we didn't release. We don't think we are going to release the pre-trained model for this. We may release the source code, but we still need to think about that. And we are working on anti-spoofing technology, but anti-spoofing is kind of lagging behind those deepfake technologies. So we think that a solution to that is watermarking techniques. We can generate watermarks to mark the original bonafide audio. We can generate watermarks for the synthetic audio. Yep. We can generate watermark to help attribute what training data was used to generate this voice or audio. So yeah, a lot of research are going on.
I lied a quick third part. Have you compared your cloning techniques to the neural transducer approaches that have been around? Have you seen the neural transducer structure?
I'm not familiar.
Okay, I'll talk offline. Thanks.
Okay. Thank you.
Right, I think we should...
And do you have rights to your performance here? You can delete it from my phone.
Okay, thank you.
So I think we should thank the speaker again and then move to the last talk.
Thank you.